The following content is produced strictly for educational, historical, and entertainment purposes. The automotive stunts, vehicle modifications, and high-speed maneuvers discussed herein are performed by trained professionals within controlled environments, utilizing advanced safety equipment and rigorous engineering protocols. This video does not constitute professional advice, mechanical instruction, or a guide for recreational driving. Attempting to replicate any of the actions described in this video is extremely dangerous and can result in severe injury, legal consequences, or death. Viewers are strongly encouraged to conduct their own due diligence regarding local traffic laws and automotive safety standards. The creators of this content assume no liability for any actions taken by viewers. 321. That is the estimated number of 1969 Dodge Chargers that were systematically destroyed, crushed, and discarded during the production of a single American television franchise. In the golden age of the Hollywood stunt, a car was not just a vehicle, it was a projectile. We often sit in darkened theaters or on our living room couches, watching a 2-ton piece of American steel soar through the air, and we take the physics for granted. We assume that because we see it on screen, it is a simple matter of hitting a ramp at a specific speed. But the reality is far more calculated, far more dangerous, and steeped in a history of trial and error that nearly cost several legends their lives. There is a specific, haunting silence that occurs in the split second a car leaves the pavement and gravity loses its grip. In that moment, the driver is no longer a pilot, they are a passenger in a ballistic trajectory. Historical trends in American filmmaking show us that the appetite for these high-stakes moments has only grown, yet the transition from raw mechanical intuition to precision computer modeling has changed the landscape of the stunt industry forever. If you have ever wondered why a car in a 1970s chase scene always seems to land on its nose, or how modern directors manage to flip a semi-truck in the middle of a Chicago street without leveling a city block, you are looking at the evolution of a uniquely American craft. The open loop we are stepping into today involves the secret engineering behind the most iconic jumps in history. We are going to look at why the General Lee required hundreds of pounds of lead ballast in the trunk just to stay level in the air, and why the most famous jump in the history of the James Bond franchise was actually calculated by a Cornell University computer in 1974. This is not just a countdown of cool clips. It is a technical autopsy of the moments that defined American action cinema. This deep dive solves a fundamental problem for the modern enthusiast and the aspiring filmmaker: the misunderstanding of practical effects versus digital deception. By the end of this masterclass, you will understand the historical trends of stunt rigging, the potential outcomes of weight distribution errors, and the case studies of the men and women who risked everything to give us 30 seconds of adrenaline. We are pulling back the curtain on the pipe ramp, the nitrogen cannon, and the Cromwell jump to show you exactly how the impossible becomes a frame-by-frame reality. To understand the magnitude of these jumps, we must first address the physics of the nose dive. In the early days of American cinema, stunt coordinators relied on launch and prey. However, gravity is a cruel mistress to a front-engine vehicle. In a standard 1960s or 70s muscle car, the engine block represents a significant portion of the total mass, located squarely over the front axle. When that car leaves a ramp, the center of gravity acts as a pivot point. Without intervention, the heavy front end will naturally pull the vehicle into a forward rotation. This is why, in many historical case studies of 1970s cinema, you see cars landing bumper first, often resulting in the immediate destruction of the vehicle's frame. To combat this, stunt engineers developed the practice of ballast loading. For a jump like the record-setting flight in the Dukes of Hazzard, crews would often weld steel plates or pour lead shot into the trunk space. The goal was to shift the center of mass rearward, attempting to balance the vehicle so it would fly parallel to the ground. The mathematical requirement for a stable flight involves calculating the parabolic trajectory, which can be expressed through the formula y stan theta 2v 2 cos 2 theta gx 2. In this equation, y represents the vertical displacement, x is the horizontal distance, theta is the launch angle of the ramp, g is the acceleration due to gravity, and v is the initial velocity. While modern stunt coordinators use software to solve for these variables, the pioneers used chalk on a garage floor and raw nerve. Consider the case study of the 1974 film, The Man with the Golden Gun. Although a British production, the stunt was performed by American drivers and conceived by American engineers at the Cornell Aeronautical Laboratory. This was the Astro Spiral Jump. The goal was to have an AMC Hornet perform a 360-degree mid-air corkscrew, while jumping across a broken bridge. This was the first time in history that a computer was used to model a car jump. The potential outcomes of being off by even 1 mile per hour were catastrophic. The engineers had to account for the moment of inertia, ensuring the car rotated at a precise angular velocity so that it would land on its wheels on the opposite side. They determined that a speed of exactly 40 miles per hour and a specifically curved shaper ramp were necessary. The success of this jump changed the historical trend of stunts from stuntman intuition to engineering precision. Furthermore, we must examine the evolution of the ramp. In the early days, a simple wooden wedge was often sufficient. However, as cars became faster and jumps became longer, the structural integrity of the ramp became a life-or-death variable. We now see the use of the pipe ramp. This is a specialized piece of equipment designed to flip a car or launch it into a roll by only catching one side of the vehicle's chassis. The engineering behind a pipe ramp involves calculating the unsprung mass of the vehicle's suspension. If the ramp is too steep, the suspension will bottom out, absorbing the energy intended for the launch and potentially causing the car to veer off course. If it is too shallow, the car fails to clear the obstacles. Modern American cinema has also introduced the nitrogen cannon, or the flipping ram. In films like The Dark Knight or the Fast and Furious franchise, you see vehicles, sometimes even massive tractor trailers, flipping end over end. This is rarely achieved by a ramp alone. Instead, a high-pressure nitrogen cannon is mounted to the floor of the vehicle. At a precise GPS-coordinated moment, the driver or a remote operator triggers the cannon, which fires a steel slug into the pavement with enough force to lift the multi-ton vehicle into the air. This shift in technology allows for stunts in tight urban environments where a 50-foot ramp would be impossible to hide. Throughout this series, we will break down 10 distinct eras and styles of the American car jump. We will look at the long jump era of the late 70s, the urban chaos era of the 90s, and the digital enhancement era of the 2000s. We will analyze the specific mechanical modifications required for these feats, such as the installation of fuel cells to prevent explosions upon impact, roll cages built from chromoly steel to protect the cabin, and 5-point harnesses that keep the driver centered during high-G maneuvers. We are going to look at the data, the crashes, and the triumphs. This is the definitive technical history of the American car jump. Preparedness meets physics in the most violent way possible. Welcome to the masterclass. To understand the jump, you have to understand the landing. We begin our deep dive in 1968, on the vertical streets of San Francisco, with a film that changed the historical trends of automotive action forever, Bullitt. Before Steve McQueen and stunt coordinator Bud Ekins took to the pavement, car chases were often filmed at slow speeds and then sped up in the editing room. Bullitt threw that playbook into the Pacific Ocean. When you see that Highland Green 1968 Ford Mustang GT Fastback and the black Dodge Charger 440 Magnum catching air on Taylor Street, you are watching the birth of the modern American car jump. Imagine if you were standing on the corner of Filbert and Taylor in 2026. You would see a steep incline that looks more like a wall than a road. Now, imagine cresting that hill at 60 miles per hour in a vehicle designed for a smooth commute, not a ballistic trajectory. In Bullitt, the potential outcomes of these jumps were not just mechanical failure but total structural collapse. The production team realized early on that a factory-spec Mustang would not survive the first day of filming. They brought in Max Balkowski, a legendary racing engineer, to perform a technical overhaul. Balkowski didn't just tune the engine. He reinforced the entire skeletal structure of the car. He installed heavy-duty springs, Coney shocks, and reinforced the strut towers with steel plating. He even added a cross-brace between the shock towers to prevent the frame from folding like an accordion upon impact. The data from these jumps is staggering. When a 3,500-pound Mustang leaves the ground and falls 10 feet through the air, it isn't just landing with its own weight. It is hitting the ground with a vertical force that can exceed 5 times the force of gravity, known as a 5G impact. In a standard car, this force would immediately blow out the oil pan, shatter the motor mounts, and send the engine block straight through the radiator. This is why you see the Mustang and Bullitt bouncing violently. That bounce is the energy of the impact being fought by the reinforced suspension. Historical trends show that the Dodge Charger actually fared worse during the shoot because it was significantly heavier. The stunt drivers had to manage a delicate balance of throttle control. If they let off the gas too early, the nose would dive. If they stayed on it too hard, they risked landing on the rear bumper and snapping the drive shaft. Moving forward to 1977, we encounter a case study in pure audacity, Smokey and the Bandit. Directed by Hal Needham, a man who was a stuntman long before he was a director. This film featured a jump that remains a masterclass in risk management. The scene involves a 1977 Pontiac Trans Am jumping a 150-foot gap over a demolished bridge. This wasn't a camera trick or a miniature model. It was a real car, a real driver, and a very real possibility of failure. The engineering behind the Mulberry Bridge jump was a pivot point in Hollywood history. Hal Needham knew that even with a powerful V8, the Trans Am wouldn't have enough velocity to clear a 150-foot gap using a standard ramp. He needed a way to guarantee the car stayed in the air longer than physics would normally allow. His solution? A nitrogen-powered rocket booster hidden in the rear of the car. This was a proto-version of the tech we see in modern 2026 blockbusters. The booster provided a momentary surge of thrust that compensated for the aerodynamic drag of the Trans Am's front-heavy design. Step by step, the team had to calculate the exact launch angle. A ramp that is too steep will send the car higher but shorter. A ramp that is too shallow will give you distance but will cause the car to clip the edge of the landing zone. They settled on a launch speed of roughly 70 miles per hour. As the car hit the ramp, the driver, Stan Barrett, had to maintain a perfectly straight line. Any steering input while the suspension is compressed on a ramp would result in a mid-air tumble. The potential outcomes of a slight steering drift are catastrophic. The car would enter a yaw rotation, meaning it would start to spin horizontally like a frisbee, leading to a side impact landing that a roll cage cannot always survive. In this era, safety protocols were largely experimental. Imagine if a driver today attempted that without a modern Hans device or a carbon fiber reinforced cockpit. In 1977, they were using basic steel tubing for roll cages and rudimentary harnesses. The impact of the Trans Am landing on the other side of the bridge was so severe that it effectively totaled the car instantly. The subframe was bent, the transmission was cracked, and the engine was pushed back into the firewall. This case study highlights a fundamental rule of movie jumps. The car you see landing is almost never the car you see driving away in the next shot. Historical trends in the late 70s also introduced the concept of the sacrificial car. For every successful jump you see on screen, there are often 3 or 4 frames left on the cutting room floor where the car disintegrated. This brings us to the most prolific destroyer of American steel in history, the Dukes of Hazzard. While technically a television show, its influence on movie stunt coordination is unparalleled. During the production of the 1979 to 1985 run, and the subsequent 2005 film, the crew went through an estimated 300 Dodge Chargers. The technical secret to the General Lee's iconic high-altitude jumps was the ballast. Because the 1969 Charger is a front-engine, rear-wheel drive car with a massive iron block engine, it is naturally nose-heavy. In early test jumps, the car would leave the ramp and immediately flip forward, landing on its roof. To solve this, the stunt crew began welding hundreds of pounds of lead plates into the trunk. This shifted the center of gravity toward the rear, allowing the car to fly level. However, this added weight increased the force of impact exponentially. Let's look at the math of the landing. If you increase the mass of a vehicle by 500 pounds of lead, you are increasing the kinetic energy, Ke equals 0.5 mv. 2. That must be dissipated upon landing. This energy doesn't just disappear. It goes into the tires, the shocks, the frame, and the driver's spine. This is why many veteran stunt drivers from this era suffer from long-term back injuries. They were effectively taking a 20-foot fall in a seated position dozens of times a week. Case studies of these jumps show an evolution in landing ramp design as well. Instead of landing on flat ground, which creates a dead-stop impact, coordinators began using transition ramps. A transition ramp is a downward-sloping landing zone that matches the angle of the car's descent. This allows the vertical energy to be converted back into forward horizontal momentum, significantly reducing the g-force of the impact and allowing the car to potentially drive away from the stunt. This transition engineering is exactly what allowed the 2026 generation of stunt performers to push the boundaries of distance even further. But even with perfect ramps and lead ballast, there is one variable that no engineer can fully control: the wind. When a car is in the air, it acts like a wing. A 1969 Charger has a lot of surface area on its underbelly. If a crosswind hits that car at the peak of its arc, it can tilt the vehicle, causing it to catch the air like a sail and flip it over. This is the hidden danger of the high jump era that many viewers never consider. As we move out of the 70s and into the high-tech era of the 80s and 90s, the physics stay the same but the tools change. we begin to see the introduction of the first computer-aided designs and the shift towards specialized stunt chassis that look like cars on the outside but are essentially trophy trucks on the inside. But before we get to the modern era of the Fast and Furious or the John Wick technical precision, we have to look at a jump so complex, so mathematically perfect, that it was actually patented. It involved a bridge, a river, and a 360-degree rotation that almost ended in disaster before the cameras even started rolling. Why did a Cornell University supercomputer spend weeks calculating the trajectory of a single AMC Hornet? And what happens when those calculations meet the reality of a muddy riverbank in Thailand? The answers lie in the shift from raw horsepower to pure geometry, and that is exactly where we are heading next. We are moving from the launch and pray era to the precision ballistics era, where a single mile per hour is the difference between a legendary shot and a recovery mission. What is the one thing that most people get wrong about the most famous jump in cinema history? You are about to find out. To understand the shift from intuition to high-level ballistics, we have to look at the single most mathematically perfect automotive feat ever recorded on film. In 2026, we have the luxury of real-time physics simulators and AI-driven telemetry, but in 1974, the tools were far more primitive. Imagine if you are Alex, a graduate student in mechanical engineering today, looking back at a grainy 1970s mainframe computer. Alex would see that the leap performed by a 1974 AMC Hornet in the film The Man with the Golden Gun was not just a stunt, it was a peer-reviewed scientific experiment. This is the Astro Spiral Jump, and its history is a case study in why precision is the only thing that separates a legend from a tragedy. Historical trends in the early 70s dictated that if you wanted a car to roll, you hit a ramp with one side of the car and hoped for the best. But the producers of the James Bond franchise wanted something that had never been seen: a 360-degree mid-air corkscrew. To achieve this, they didn't go to a daredevil. They went to the Cornell Aeronautical Laboratory in Buffalo, New York. Specifically, they worked with Raymond McHenry. McHenry had developed a computer program called the Highway Vehicle Object Simulation Model. This was one of the first times a digital environment was used to predict the potential outcomes of a high-speed vehicle collision. The technical challenge was staggering. The car had to launch from a curved ramp, rotate exactly 360 degrees along its longitudinal axis, and land on its wheels on a second curved ramp across a river. If the car rotated only 350 degrees, the suspension would collapse on the edge of the rim. If it rotated 370 degrees, the car would cartwheel into the mud. The mathematical requirement involves solving for angular momentum. In physics, angular momentum is the product of the moment of inertia and the angular velocity. For the AMC Hornet, the engineers had to determine the exact speed, 40 miles per hour, down to the decimal point. The ramp itself, known as the shaper, was a masterpiece of geometry. It wasn't a flat surface. It featured a specific parabolic curve that forced the car's suspension to compress and then release in a way that initiated the roll at the precise millisecond the wheels left the metal. To ensure the center of gravity was perfectly centered, the driver, Bumps Willard, had to sit in the middle of the car. The steering wheel and pedals were relocated to a central position to prevent the weight of a human being on the left side from causing a wobble in flight. The potential outcomes of even a 5-pound weight discrepancy would have meant a failed rotation. When you watch that jump today, you are seeing a one-take success that was so accurate, it was actually patented as an invention. Now, contrast that with the 1990s, where the scale of jumps shifted from surgical precision to sheer brute force mass. Take the case study of the 1994 film Speed. Imagine if you were tasked with jumping a 15,000-pound GM 5303 city bus over a 50-foot gap in a freeway. This is a vehicle with the aerodynamic profile of a brick and the structural flexibility of a wet cardboard box. Historical trends in cinema usually involved using miniatures for something this massive, but director Jan de Bont insisted on a practical jump. The physics of a bus jump are fundamentally different from a muscle car. The primary issue is the wheelbase and the overhang. In a standard bus, the distance from the front bumper to the front wheels is significant. As the bus leaves a flat ramp, gravity begins to pull the nose down immediately. By the time the rear wheels leave the ramp, the bus is already in a nosedive. The engineering team had to reinforce the entire front subframe of the bus to ensure the engine didn't tear through the floor upon impact. They also had to calculate the suspension rebound. In the film, the bus is shown jumping a gap on a level freeway. In reality, physics dictates this is impossible without a launch angle. If a bus travels horizontally at 70 miles per hour, gravity will pull it down at a rate of 32 feet per second squared the moment it loses ground support. To clear a 50-foot gap, the bus would have dropped several feet, slamming into the opposite edge of the concrete. To solve this, the stunt crew built a massive hidden ramp that was masked by the camera angle. The bus hit that ramp at approximately 61 miles per hour. One of the most shocking data points from this jump is that the bus actually reached a height of 20 feet in the air. Upon landing, the impact was so severe that the driver's seat, which was reinforced and mounted on a specialized suspension system, broke. The bus did not just land. It bounced nearly 3 feet back into the air because the tires were inflated to a high PSI to prevent them from debeating from the rims under the G-load. This is a prime example of a case study where the potential outcomes of failure were mitigated by over-engineering the vehicle's skeleton. When we look at these two jumps, the Hornet and the bus, we see the two pillars of American stunt work: the mathematical spiral and the heavy impact leap. But as we move into the 2000s, the technology changed again. We began to see the rise of the nitrogen cannon, which we touched on earlier, but the application became far more sophisticated. Imagine if you were watching the filming of the 2005 film The Island. Stunt coordinators were no longer satisfied with just jumping cars. They wanted the cars to jump while being pursued by other vehicles in a multi-car pileup. This required the invention of the flipper car. Unlike the ramps used in Bullet or Smokey and the Bandit, a flipper car is a vehicle equipped with a hydraulic cowcatcher that can be triggered to lift a pursuing car into the air at a precise moment. This allows for a jump to occur without a visible ramp on the ground. The engineering of a flipper car involves high-pressure hydraulics that can exert thousands of pounds of force in less than half a second. This is the transition point where car jumps stopped being a solo performance and became a choreographed dance of physics. We started seeing the use of remote control systems. In many modern case studies, the car performing the jump has no driver at all. Instead, it is steered by a technician in a follow car using a high-frequency radio link. This allows the car to hit the ramp at speeds that would be lethal for a human occupant, pushing the limits of what the frame can handle. But even with all this tech, something was missing. The audience started to get used to the spectacle. They wanted more than just height, they wanted weight, and they wanted it to feel dangerous. This led to one of the most insane moments in recent history, involving a semi-truck, a city street in Chicago, and a man named Christopher Nolan. Why did the production team of The Dark Knight decide to actually flip a 40-foot tractor-trailer end-over-end instead of using CGI? And what was the specific mechanical failsafe that prevented the truck from crushing the surrounding skyscrapers? To understand that, we have to look at the geometry of the vertical flip, a maneuver so violent it required a custom-built steam-powered piston that could launch 20 tons of steel into the air. If you thought jumping a Mustang was hard, wait until you see the math behind flipping a skyscraper on wheels. The shift from the horizontal to the vertical is where the masterclass gets truly dangerous, and that is where we are going in the next part. When we talk about shifting from horizontal distance to vertical rotation, we are entering the realm of terminal mass. Imagine if you are Jordan, a technical director in 2026, tasked with recreating the most ambitious heavy vehicle stunt in the history of the United States film industry. You aren't looking at a nimble muscle car or a modified sedan. You are looking at a 20-ton Peterbilt tractor-trailer. This is the case study of The Dark Knight, specifically the 2008 sequence filmed on LaSalle Street in Chicago. To understand the insanity of this jump, you have to realize that this was not a jump in the traditional sense. It was a vertical inversion. Historical trends in Hollywood usually relied on miniatures for something of this scale. If you wanted a semi-truck to flip end over end, you built a 1/12 scale model and used high-speed cameras to trick the eye. But Christopher Nolan and stunt coordinator Chris Corbould decided to defy those trends. They wanted the weight of a real truck to interact with the real pavement of a major American city. The potential outcomes of a miscalculation here were not just the ruined shot. They included the collapse of underground utility vaults, or the truck crashing through the windows of the surrounding financial district. The engineering solution was the nitrogen-powered steam piston. Think of this as a massive high-pressure cannon mounted vertically inside the trailer. Step by step, the team had to calculate the exact force required to lift 20,000 pounds of steel into the air. The physics behind this is governed by the principle of torque in the center of mass. If the piston fired too far forward, the truck would just slide. If it fired too far back, the trailer would snap off the fifth wheel hitch and crush the cab. The calculation for the force F required to initiate the flip involves the mass m of the truck and the distance d from the pivot point to the piston. Thus if d. They had to generate enough torque tau to overcome the truck's massive inertia. The team used a large steel cylinder filled with high-pressure nitrogen. When the driver, Jim Wilkie, triggered the release, a massive steel slug was hammered into the asphalt. The reaction force was so violent that it sent the entire rear of the trailer soaring into the air. One data point often overlooked is the reinforcement of the truck's frame. A standard semi-truck frame is designed for longitudinal strength, pulling weight forward. It is not designed for the vertical stress of being launched into the air. The crew had to weld massive steel I-beams into the trailer's substructure to ensure it didn't fold in half the moment the piston fired. Imagine if that piston had encountered a soft patch in the road. The slug would have simply buried itself in the dirt, and the truck would have stayed grounded while the internal pressure blew the trailer apart. To prevent this, the Chicago City engineers had to verify the thickness of the concrete on LaSalle Street, ensuring it could withstand the localized pressure of several thousand pounds per square inch. This is the difference between a movie stunt and a structural engineering project. Now let's pivot to a different kind of verticality: the bridge jump in the 2000 remake of Gone in 60 Seconds. This case study features the legendary Eleanor, a 1967 Ford Mustang GT500. The scene calls for the car to jump over a massive pileup of vehicles on the Vincent Thomas Bridge in San Pedro, California. This jump is a prime example of the historical trend of transitioning from pure practical stunts to hybrid stunts. While the car was launched off a physical ramp, the height and the landing were assisted by early 2000s digital technology. However, the practical foundation of that jump was still incredibly dangerous. The car hit a ramp at approximately 70 miles per hour. One of the most critical step-by-step details in a bridge jump is the approach. In 2026, we might use automated throttle control, but in 2000, the driver had to manage the tramlining effect. When a car approaches a ramp at high speed, the grooves in the bridge's concrete can catch the wide tires of a Mustang, pulling the car off-center. If the car hits the ramp at an angle, it will roll mid-air. The landing of the Eleanor Mustang provides a fascinating data point on vehicle survival. In the film, the car lands and continues to drive. In reality, the car used for the primary jump suffered a total suspension failure. The front struts were pushed through the hood, and the rear axle was bent beyond repair. This highlights the rule of the hero car versus the stunt car. For a jump of this magnitude, the production built multiple versions of Eleanor. The stunt versions were stripped of all non-essential weight, interior trim, glass, and even the passenger seat, to keep the car as light as possible. This reduced the KE equals 0.5 times m times v. 2. Kinetic energy upon landing, giving the frame a better chance of remaining intact for the duration of the shot. But what happens when you don't have a static ramp? This leads us to the high-stakes world of the moving platform jump, famously seen in Bad Boys 2. Imagine if you are on a high-speed highway in Miami. You are driving a Ferrari 550 Maranello, and cars are being thrown at you from a moving car carrier. This stunt, coordinated by Henry Kingi, involved a technical concept called relative velocity. Step by step, the team had to synchronize the speed of the car carrier and the speed of the trailing vehicles. If the carrier is traveling at 60 miles per hour and it drops a car, that car is also traveling at 60 miles per hour relative to the ground. For the following cars to jump over or maneuver around these obstacles, they have to be traveling at a significantly higher speed, often exceeding 90 miles per hour in a congested environment. The potential outcomes of a timing error are a multi-car collision that the camera might not even catch. They used pipe ramps hidden on the back of the car carrier. A pipe ramp is essentially a rail that catches the underside of the jumping car, guiding it into a specific trajectory. The data from the Bad Boys 2 shoot showed that the pipe ramps had to be adjusted for every single car that was launched. A heavy sedan requires a different ramp angle than a lighter coupe. If the ramp is too narrow, the car will slide off the side and flip. This is where we see the introduction of the dead man's switch for the nitrogen cannons. If the driver feels the car is not centered on the ramp, they can release the switch to abort the jump, but once the wheels leave the metal, they are at the mercy of the math. As we look at these vertical and high-speed maneuvers, we see a pattern. The American movie jump evolved from a simple test of nerves into a complex orchestration of pressure, mass, and timing. We went from jumping a Mustang over a hill in San Francisco to flipping a 20-ton truck in the middle of a skyscraper canyon. But there is one technique that remains the holy grail of car stunts. A maneuver that combines a high-speed jump with a controlled crash that is so violent, it requires the car to be literally blown apart from the inside. What happens when you combine a 100-foot leap with a 360-degree barrel roll? And why did the crew of the 2024 The Fall Guy need to break a Guinness World Record just to get the perfect shot? The secret lies in a piece of tech called the cannon car, and the way it uses an explosive charge to kick the ground away from the vehicle. We are moving into the era of the high-speed roll, where the jump is just the beginning of the chaos. If you think you've seen a car flip, wait until you see how they do it when the goal isn't just to land but to disintegrate. That is where we are heading in Part 5. The concept of the cannon car is often misunderstood as a simple explosion underneath a vehicle, but in the reality of high-level stunt engineering, it is a masterclass in controlled pneumatic power. To understand the sheer violence of a car disintegration stunt, we must look at the 2024 case study of the film The Fall Guy. In this production, stunt driver Logan Holiday set a new Guinness World Record by performing 8.5 barrel rolls in a single jump. This wasn't achieved with a ramp. Instead, it used the most advanced iteration of the nitrogen cannon ever seen in American cinema. Imagine if you are Taylor, a lead stunt rigger in 2026. You are standing on a beach in Australia, but you are working for a major US studio. You have a modified Jeep Grand Cherokee, and your goal is to make it flip as many times as possible across the sand. The historical trends of the 1980s would have suggested a pipe ramp, but a ramp is visible to the audience and limits the number of rotations. Instead, Taylor uses a cannon car setup. Step by step, the team installs a high-pressure nitrogen tank in the rear of the vehicle, connected to a vertical steel tube that passes through the floorboards. Inside that tube is a solid steel slug, often weighing between 40 and 80 pounds. The physics of this maneuver are precise. At a specific GPS-coordinated moment, the driver or a remote technician triggers a high-speed solenoid valve. This releases approximately 3,000 to 4,000 psi of nitrogen pressure instantly. The potential outcomes of this pressure release are dictated by Newton's third law. For every action, there is an equal and opposite reaction. The slug is hammered into the ground with enough force to lift the entire side of the vehicle. However, because the cannon is mounted off-center, it creates a massive torque moment. This torque initiates an angular velocity that sends the car into a barrel roll. The data from the Fall Guy shoot showed that the car had to hit a specific speed, roughly 60 miles per hour, to maintain enough linear momentum to carry it through 8 full rotations. If the speed were 55 miles per hour, the car might have stalled mid-roll and landed on its roof. If it were 65 miles per hour, the centripetal force might have ripped the vehicle apart before the cameras could capture the grace of the movement. To ensure the car disintegrates in a way that looks spectacular but remains safe for the driver, the structural engineering must be modified. This is where we see the transition from a factory vehicle to a stunt shell. In a masterclass of vehicle preparation, every piece of glass is replaced with Lexan or removed entirely. The interior is gutted, leaving only a specialized racing seat and a roll cage. The roll cage is the most critical component. It is typically constructed from 4130 chromoly steel tubing, which offers a high strength-to-weight ratio. The tubing is TIG welded into a 6-point or 8-point configuration that ties into the main frame rails. However, a rigid car is a dangerous car for a human occupant. Historical trends in safety engineering have taught us that if the car does not deform, the kinetic energy is transferred directly to the driver's body. To manage this, stunt riggers use the principle of energy dissipation through sacrificial components. They will pre-cut certain body panels or use plastic snap-on parts that are designed to fly off upon the first impact. This creates the visual of a car disintegrating, while the core safety cell remains intact. When you see a door fly off or a bumper tumble through the air, that is energy leaving the system. It is a calculated reduction in the total force that the driver Logan Holiday has to absorb. Let's look at the case study of the 2006 film Casino Royale. For the iconic 7-roll crash of the Aston Martin DBS, the production team faced a unique problem. The DBS was so well engineered and had such a low center of gravity that it refused to flip, even when hitting a ramp at high speeds. The car would simply land and stay flat. To solve this, the team had to install a nitrogen cannon. The data from that stunt revealed a significant challenge: the weight of the Aston Martin. Because the car was heavier than a standard stunt vehicle, the nitrogen cannon had to be tuned to a higher PSI. The result was a record-breaking series of rolls that occurred so fast the human eye could barely track them. The angular momentum was so high that the driver experienced G-forces comparable to a fighter pilot in a high-speed maneuver. In 2026, we also have to consider the role of the fuel system in these high-velocity jumps. A standard fuel tank is a bomb waiting to happen during a multi-roll stunt. Stunt cars use a specialized component called a fuel cell. Unlike a metal tank, a fuel cell is a flexible bladder housed inside a steel or aluminum container. It is filled with an open cell foam that prevents the fuel from sloshing. This sloshing is actually a major variable in car jumps. If several gallons of gasoline shift to one side of the tank while the car is in the air, it changes the center of mass and can cause an unwanted tilt. The foam inside a fuel cell keeps the weight distributed evenly and, more importantly, prevents the fuel from atomizing and igniting if the cell is punctured. The step-by-step preparation for a disintegration jump also involves the removal of the engine's cooling system. For a 5-second stunt, you don't need a radiator or a water pump. These are heavy components filled with scalding liquid that can spray the driver upon impact. By removing the radiator and using a total loss oil system, riggers can shave 100 pounds off the front of the car, which significantly improves the flight characteristics. Imagine if you were the driver in this scenario. You are strapped into a 5-point harness so tightly that you can barely breathe. Your head is secured by a Hans, head and neck support, device to prevent your skull from snapping forward during the 10G impact of the first roll. You are wearing a multi-layer fire suit made of Nomex. As you approach the hit mark at 65 miles per hour, your hand is on a trigger or you are waiting for the computer to fire the cannon. The moment the cannon fires, the world disappears into a blur of sky and ground. The noise is deafening, the sound of the nitrogen release followed by the screeching of metal on pavement. Historical trends show that the most successful disintegration shots are those where the car lands on a transition surface, like sand or loose dirt, rather than concrete. This is because the dirt allows the car to dig in, which increases the torque and creates more spectacular rolls. On flat concrete, the car tends to slide more than it rolls, which can lead to a less dramatic visual. This brings us to the technical evolution of the Cromwell jump, a maneuver where the car is launched vertically and then intentionally stalled in midair to create a flat-back landing. This is often used in American war movies or post-apocalyptic films to show a vehicle being destroyed by an explosion. The engineering involves a dual cannon setup, one to launch the car and another to kick the rear end up at the peak of the arc. But as we master the art of the roll and the disintegration, a new challenge has emerged in the world of 2026 stunt coordination. Audiences are no longer satisfied with seeing a car flip in an open field. They want to see a car jump through a building, or better yet, jump while the driver can't see where they are going. This is the blind jump, and it is one of the most terrifying developments in modern action cinema. How does a stunt driver hit a 6-foot-wide ramp at 80 miles per hour when their entire windshield is blacked out by smoke or fire? The answer involves a hidden technology that allows a second driver to control the car from a completely different position, sometimes even from a pod mounted on the roof. We are moving from the driver being in control to the driver being a passenger in their own stunt. What happens when the person steering the car isn't actually inside the car? We are diving into the pod car and the blind high-speed leap in the next part of this masterclass. The physics of remote control stunt driving are about to change everything you think you know about car chases. The pod car is a marvel of modern stunt engineering that essentially splits the act of driving into two distinct layers. Imagine if you are Marcus, a stunt coordinator in 2026, and you are tasked with filming a high-speed car jump where the actor inside the vehicle must appear to be in total control, even as the car is performing a life-threatening maneuver. In the past, you would have used a low loader or a tow cable, but that limits the speed and the physics of the jump. Instead, you build a pod car. This involves mounting a secondary driving station, or a pod, onto the roof or the rear of the vehicle. This pod is a self-contained roll cage equipped with its own steering wheel, pedals, and gear shifter, all of which are mechanically or hydraulically linked to the car's primary systems. The engineering required to make a pod car jump ready is incredibly complex because of the center of gravity. Historical trends in automotive design emphasize a low center of gravity to improve handling. When you add a 500-pound steel cage and a 200-pound driver to the roof of a car, you are fundamentally altering the vehicle's stability. The height of the center of gravity, denoted as h, CG, can be calculated by the sum of the moments of each component divided by the total mass. By moving that mass 5 feet higher, you increase the likelihood of a rollover upon landing. To compensate for this, Marcus and his team must widen the vehicle's track using wheel spacers and install significantly stiffer anti-roll bars. If the suspension is not tuned to handle the top-heavy load, the car will catch a corner upon landing and initiate a catastrophic side roll. Case studies from the production of Mad Max Fury Road show the peak of this technology. Stunt coordinator Guy Norris used pod cars to allow actors to perform in the middle of high-speed chases across the Namibian desert. However, when these cars were required to jump, the technical challenges doubled. The driver on the roof is exposed to much higher G-forces, because they are further from the roll center of the vehicle. Imagine the whip crack effect when a car lands a jump. While the actor inside feels a vertical jolt, the driver on the roof experiences a magnified arc of motion. This requires the pod to be mounted with reinforced grade 8 bolts and specialized vibration-dampening pucks to prevent the entire driving station from shearing off the roof during a high-G impact. Step by step, the installation of a pod car starts with the hydraulic steering linkage. In most 2026 stunt builds, they use an orbital valve system similar to what you find in heavy agricultural machinery. This allows for steer-by-wire capability or a hydraulic override where the pod driver has total control regardless of what the actor does with the steering wheel inside. The potential outcomes of a hydraulic failure during a jump are severe. If the steering locks while the car is in the air, the driver cannot correct the landing angle, leading to a diagonal impact that will likely shatter the axle. This brings us to the blind jump, a technique where the driver has zero visibility of the road ahead. Imagine if you were in the seat of the Batmobile in the 2022 film The Batman. During the iconic chase with the Penguin, the Batmobile leaps through a massive explosion of fire and debris. For this shot, stunt driver Rob Alonso had to hit a ramp while his vision was completely obscured by a wall of flame and specialized cinematic smoke. In 2026, we solve this using low-latency digital telemetry and head-up displays. The driver wears a VR-style headset that is fed a real-time stream from a camera mounted on the front bumper, low enough to see under the smoke. However, even with the best cameras, a blind jump requires a high level of mathematical preparation. The team must calculate the approach velocity and the drift angle long before the car hits the ramp. If the car is traveling at 80 miles per hour, it covers 117 feet per second. A delay of just 1/10 of a second in the video feed means the driver is seeing a world that is 11 feet behind where they actually are. Historical trends in stunt failures often point to this latency as a primary cause of accidents. To mitigate this, engineers use fiber optic cables for the camera feed rather than wireless transmitters, reducing the lag to less than 5 milliseconds. Let's look at the data from a case study involving a blind leap in an urban environment. When a car jumps through a fire or a wall, the air density around the vehicle changes instantly. The heat from an explosion can thin the air, reducing the lift or drag on the car's body panels. This can cause the car to drop faster than the parabolic equations predicted. The calculation for the force of gravity remains F equals mg, but the aerodynamic drag force D equals 0.5 rho v. 2. C. D. A is suddenly altered because the air density rho drops as temperature rises. Stunt coordinators must overspeed the approach to ensure the car doesn't fall short of the landing ramp due to this loss of atmospheric support. In some extreme scenarios, even a pod car is too dangerous. This is where the remote drive system comes in. In 2026, we see the rise of the Phantom driver. This is a car equipped with high-torque actuators on the steering column and brake pedal, controlled by a driver sitting in a simulated cockpit in a van following a safe distance behind. This allows for jumps that are essentially suicide missions for a human occupant. The potential outcomes here are purely mechanical. If the radio frequency is jammed or suffers from interference from the city's power grid, the car becomes a 4,000-pound unguided missile. Imagine if you were watching a remote-controlled car jump across a 60-foot gap between two shipping containers. The operator must manage the throttle with a level of precision that is difficult to achieve without the physical feedback of the seat. They rely on haptic feedback systems in their remote rig to feel the vibration of the engine and the tension in the tires. This technology has allowed American cinema to perform jumps that were previously deemed impossible, such as a car performing a mid-air rotation while trailing a 50-foot plume of ignited fuel. The integration of pod cars and remote systems has fundamentally changed the historical trends of the movie chase. We no longer see the jump as a standalone event. It is now a seamless part of a continuous shot where the camera stays on the actor's face as they fly through the air. But this level of immersion comes with a hidden cost. The complexity of the rig makes the car much more fragile. Every wire and hydraulic line is a potential point of failure. If the landing is too hard, a single loose connection can kill the engine, leaving the car dead in the water in the middle of a high-speed sequence. As we master the technology of the pod and the remote leap, we have to face the next evolution in the American car jump. It is no longer enough to jump over a bridge or through a fire. The modern audience wants to see the car interact with the environment in ways that defy the laws of physics. We are moving into the era of the vertical wall ride and the building-to-building leap. How do you jump a like in hypersport between 3 skyscrapers in Abu Dhabi? And what happens to the suspension when you land on a marble floor after a 100-foot flight? We are leaving the pavement behind and heading into the sky for the most expensive jumps ever caught on film. The engineering of the skyscraper jump is where the masterclass enters the stratosphere, and the physics of terminal velocity are about to become your biggest enemy. Why did the production team of the Fast franchise have to build a custom-weighted chassis just for a jump that lasted 4 seconds? The answer is buried in the science of the descent, and it is coming up in Part 7. The vertical frontier of American stunt work reached its zenith when cinema moved from jumping over dirt mounds to jumping between the clouds. To understand the science of the descent, we must look at the most ambitious skyscraper-to-skyscraper leap in history, the Etihad Towers sequence from the 2015 film Furious 7. Imagine if you are David, a structural engineer in 2026, analyzing the feasibility of a $3.4 million Lykan Hypersport traveling through the glass of a 45th floor penthouse. David would tell you that the primary enemy of this jump isn't the distance, but the invisible fluid dynamics occurring between the buildings. Historical trends in urban stunt work usually involved ground-level chases, but the shift to high-altitude jumps introduced a phenomenon known as the Venturi effect. When air is forced between two large structures like skyscrapers, it accelerates, creating a localized high-velocity wind tunnel. If a car leaves the sanctuary of a building and enters this high-speed airstream, the potential outcomes change instantly. The car is no longer just a projectile, it becomes an airfoil. A supercar like the Lykan Hypersport is designed with a flat underbody to create downforce, pulling the car toward the road. However, in mid-air, if the pitch of the car tilts upward by even a few degrees, that flat bottom acts like a wing generating lift. This lift can stall the car's forward momentum or worse, cause it to flip backward in a maneuver known as a blow-over. Step by step, the production team had to mitigate this risk. They didn't use a real Lykan for the actual flight. They built 6 specialized stunt shells. These were not just fiberglass bodies on empty frames. They were custom-weighted chassis designed with a deliberate forward-leaning center of mass. By placing heavy lead weights in the front nose cone, the engineers ensured that the car would maintain a slightly nose-down attitude throughout the flight. This uses gravity to counteract any aerodynamic lift. The mathematical model for the flight path is a parabola, but it is heavily influenced by the initial velocity v and the angle of launch theta. The equation for the horizontal range are in this context must account for the height of the landing floor relative to the launch floor.
R równa się
G cos
theta
2 plus 2g. In this case study, the height h was effectively 0 or slightly negative as the car jumped to a lower floor in the adjacent tower. To ensure the car didn't tumble, the stunt riggers used a specialized launch rail. Unlike the dirt ramps of the 70s, this was a precision machine steel track that ensured both front wheels left the building at the exact same microsecond. If one wheel encountered more friction than the other, the car would enter a yaw rotation, causing it to spin like a top as it crossed the 100-foot gap. Once the car clears the gap, it faces the problem of the landing surface. In the film, the Lykan smashes through a glass curtain wall and lands on a polished marble floor. Imagine if you were the driver in this scenario. You are hitting a surface with a friction coefficient μ that is significantly lower than asphalt. Marble is essentially a sheet of stone that, when covered in glass dust from the broken windows, becomes as slick as an ice rink. The kinetic energy Ke equals 0.5 mv. 2. Must be dissipated instantly. If the car lands at 60 miles per hour, the tires have almost zero grip to initiate braking. This is why, in the case study of the Etihad jump, the car continues to slide through the interior of the building. The stunt engineers had to calculate the braking distance on a low-friction surface to ensure the car didn't fly out the opposite side of the second building. They used high-performance soft compound racing tires that were chemically treated to be sticky even on stone. The impact force of landing after a 100-foot horizontal flight is also a major variable. When the car hits the floor, the suspension is compressed to its absolute limit. In a standard Lykan, the carbon fiber suspension components would shatter under the stress. The stunt cars were instead fitted with long-travel off-road shocks, hidden inside the supercar body. These shocks are designed to absorb thousands of pounds of force per square inch, allowing the car to land and maintain its structural integrity. The potential outcomes of using factory suspension would have been the car bottoming out, and the frame rails hitting the marble, causing the car to bounce uncontrollably into the ceiling. As we look at the evolution of these high-altitude stunts, we must also examine the case study of the bridge swing in Fast and Furious 9. This jump took the concept of the leap and added the element of tension. The scene involves a car being caught by a falling cable and swinging across a chasm like a pendulum. This is a masterclass in the physics of centripetal force and tension. The tension T in the cable at the bottom of the arc can be calculated using the formula T equals theta L mv. 2. Where m is the mass of the car, g is gravity, v is the velocity at the bottom of the swing, and L is the length of the cable. The historical trends of American stunts usually avoided such complex physics, but for F9, the production used a real vehicle on a massive crane rig. They had to ensure that the attachment point on the car, the hitch, was welded directly to the primary roll cage. If it had been attached to the frame or the bumper, the force of the swing would have literally ripped the car in half, leaving the chassis behind while the body sailed away. Imagine if you were the rigger for this stunt. You have to account for the stretch of the steel cable. Under the load of a 4,000-pound car swinging at 50 miles per hour, a standard cable can stretch several feet. This means the car would have hit the ground or the side of the cliff before reaching the peak of its arc. The team used non-stretch synthetic cables, often used in aerospace, to ensure the arc remained mathematically perfect. These building-to-building and chasm-crossing jumps represent the peak of what we call the environmental interaction era. It is no longer about the car alone. It is about how the car survives the collision with architecture and the elements. We have seen cars jump through fire, over water, and between towers. But as the stunts became more extreme, a new question arose. What happens when the car is no longer enough to protect the occupant? The industry began to look at stunts where the jump is only the first stage of the action. What happens when the driver has to exit the vehicle mid-air, or when the car itself is launched from the back of a moving cargo plane at 10,000 feet? We are moving from the skyscraper leap to the aerial insertion. The physics of terminal velocity and parachute deployment for a 2-ton vehicle are about to redefine the limits of American cinema. Why did the production of Furious 7 actually drop 5 real cars out of a 130 transport plane over the Arizona desert? And how did they prevent the cars from spinning into a dead man's roll before the chutes opened? The secret lies in the science of the drogue chute and the stabilizer fins. We are going from the urban canyon to the open sky, where gravity is the only constant. That is where we are heading in Part 8. The most insane car jump in history isn't over a bridge. It is from the clouds. Imagine if you are Sarah, a lead aerial stunt consultant in 2026, standing on the cargo ramp of a Lockheed C-130 Hercules at 12,000 feet. Below you is the vast, shimmering heat of the Arizona desert. Behind you sit 5 heavily modified vehicles, including a 1970 Dodge Charger and a Subaru WRX STI. In a few seconds, these 2-ton machines will be pushed into the void. This is not a CGI sequence. This is the technical reality of the aerial insertion stunt from the film Furious 7, a moment that redefined the historical trends of what we consider a car jump. To understand the sheer complexity of dropping a car from the sky, we must first address the physics of terminal velocity. When a vehicle leaves the stable platform of an aircraft, it enters a state of freefall where gravity is the primary accelerating force. However, unlike a human skydiver who can arch their back or move their limbs to control their orientation, a car is a rigid, aerodynamically unstable brick. The terminal velocity of a standard car, the point where the upward force of air resistance equals the downward force of gravity, is typically between 130 and 150 miles per hour. The equation for this velocity is T equals ρc d 2 milligrams. In this masterclass of physics, m is the mass of the car, g is the acceleration due to gravity, ρ is the density of the air, a is the projected frontal area, and c, d, is the drag coefficient. Because a car's c, d, is relatively high and its mass is significant, it gains speed rapidly. The potential outcomes of a car falling without stabilization are catastrophic. Within seconds, the vehicle will enter what stunt performers call a dead man's roll. Because the center of gravity is not perfectly aligned with the center of pressure, the car will begin to tumble along all 3 axes: pitch, roll, and yaw. This tumbling creates massive centrifugal forces that can actually rip body panels off the car before it even hits the ground. Step by step, the production team, led by stunt coordinator Jack Gill, had to engineer a way to keep these cars upright. The solution was a 2-stage deployment system. First, as the car is pulled out of the plane by a static line, a small drogue chute is deployed. This is a 6-foot diameter pilot chute that stays attached to the rear of the car. Its sole purpose is to provide directional stability. Think of it like the feathers on an arrow. It creates just enough drag at the back of the vehicle to keep the nose pointed toward the earth. Historical trends in military airdrops show that without this drogue, the car would likely flip end over end, causing the main parachutes to tangle in the chassis upon deployment. Case studies from the Arizona shoot reveal that the cars were mounted on specialized wooden pallets or skids. These skids are designed to absorb the initial shock of the exit and provide a flat surface for the car to slide off the ramp. Imagine if one of the tie-down straps snapped a fraction of a second too early. This would cause a dirty exit, where the car rotates while still inside the fuselage of the C-130. The potential outcomes include the car striking the interior of the plane, which could result in a total loss of the aircraft and the crew. To prevent this, the release mechanism is often a pneumatic system that fires all four corner locks simultaneously, ensuring a perfectly level departure. Once the car has fallen for approximately 5,000 feet and reached a stable terminal velocity, the main deployment sequence begins. In 2026, Sarah would use a barometric trigger, a device that senses air pressure changes to determine altitude, to fire the main chutes. For a 3,500-pound vehicle, you cannot use a standard parachute. The production utilized military-grade G11 parachutes, which are roughly 100 feet in diameter. The force of these chutes opening is immense. We are talking about a deceleration from 140 miles per hour to roughly 20 miles per hour in a matter of seconds. This creates a massive G-load on the vehicle's roof and pillars. To handle this, the stunt cars were built with an internal exoskeleton. The roll cage wasn't just for the driver. It was the primary structural load-bearing member for the parachute lines. The lines were not attached to the bodywork, which would have simply been ripped off, but were bolted directly to the chromoly steel tubes of the cage. This ensures that the weight of the car is distributed evenly across the suspension during the descent. Data from the production shows that even with these precautions, the landing is the most dangerous phase. A car descending at 20 miles per hour under a parachute is still hitting the ground with a force comparable to a low-speed collision. If the wind catches the parachute right at the moment of impact, it can drag the car across the desert, flipping it repeatedly. To mitigate this, the team used quick-release cutters. The moment the suspension compresses upon hitting the dirt, a small explosive charge or a mechanical blade severs the parachute lines, allowing the chute to fly away while the car remains stationary. In the world of 2026, we also have to consider the role of camera technology in these jumps. For the Furious 7 drop, 3 camera planes and several helmet-mounted cameras on skydivers were used to track the cars. The skydivers had to fly in close formation with the falling vehicles, maintaining a distance of only 10 to 15 feet, while traveling at 140 miles per hour. This requires a level of relative velocity management that is equivalent to precision formation flying. If a cameraman gets too close, the wake turbulence from the falling car could cause them to lose control. The aerial insertion represents the absolute limit of practical car stunts. It combines the disciplines of aeronautical engineering, ballistics, and professional skydiving. But while dropping a car from a plane is a feat of logistics, there is another type of jump that relies on a different kind of precision, the kind that happens in the middle of a crowded city, where the car must jump through a moving target. What happens when you need to jump a car not just over a bridge, but through the open doors of a moving freight train? We are moving from the verticality of the sky back to the horizontal chaos of the tracks. The timing required for a train jump is measured in milliseconds, and the potential outcomes of a miss involve a collision with thousands of tons of moving steel. This is the train gap leap, and the engineering behind it involves synchronized GPS tracking and high-torque electric motors that can accelerate a car to 80 miles per hour in a confined space. How did the crew of the 2026 blockbuster Neon Drift manage to jump a fleet of electric supercars over a moving locomotive in downtown Chicago without a single centimeter of error? The secret involves a technology called phase-locked loop velocity control, and it is the only reason the drivers survived. We are heading into the most synchronized car jump in history in Part 9. The tracks are hot, and the clock is ticking. The concept of phase-locked loop velocity control is traditionally found in the world of telecommunications and high-end radio frequency engineering, but in the landscape of 2026 stunt coordination, it has become the backbone of the most dangerous synchronized jumps ever attempted. To understand the train gap leap, you have to look at the math of 2 moving targets. Imagine if you are Tyler, a systems engineer working on the set of the 2026 production Neon Drift in the heart of Chicago. You are not just looking at a car hitting a ramp. You are looking at a car that must intersect a 6-foot wide opening in a freight train traveling at 60 miles per hour. If the car is even 1/1000th of a second off its mark, it will collide with a wall of moving steel that has enough mass to flatten a suburban house without slowing down. Historical trends in cinema, like the train heist in Fast 5, showed us the potential outcomes of physical timing. In the 2011 case study, the stunt was performed with a combination of a real car and a specialized flatbed. However, by 2026, the complexity has scaled. In the Chicago sequence, the vehicle, a custom-built electric stunt rig with 1,200 horsepower, uses phase-lock loop velocity control to slave its acceleration curve to the speed of the train. The car and the train are both equipped with differential GPS units that provide centimeter-level accuracy. Tyler, sitting in the command van, monitors the phase lock. The computer calculates the exact moment the car needs to leave the starting line, so that its parabolic arc peaks exactly when the gap in the train passes the intersection point. The physics of a train jump are complicated by the Bernoulli effect. As a massive train moves through the air, it creates a zone of high-velocity, low-pressure air along its sides. When a car jumps toward or over a moving train, it enters this turbulent slipstream. This air pressure differential can exert thousands of pounds of lateral force on the car, pulling it toward the train or pushing it away. To counter this, the engineering team on Neon Drift had to add active aerodynamic surfaces, small high-speed actuators on the car's underbody that adjust in milliseconds to stabilize the flight. The calculation for the lateral drift Z depends on the velocity of the train v, t, and the air density ρ.
Lateral. Midem pederovi.
T, 2,
Actini. Y.
In this equation, A is the side surface area of the car and C,
Y.
is the lateral force coefficient. If the car has a large surface area like a modern SUV, the force of the train's weight can literally blow the car off course mid-air. Step by step, the team must test the car's reaction to these forces using high-speed wind tunnel simulations. One of the most critical data points in a train jump is the friction coefficient of rubber on steel. In many historical case studies, the car must drive onto or off a moving train car. Steel tracks and flatbeds have a friction coefficient μ that is roughly 0.1 to 0.2 when wet, compared to 0.7 for dry asphalt. This means that if the driver applies the brakes too hard upon landing on the train, the wheels will lock instantly, and the car will slide off the edge like it is on ice. To prevent this, stunt cars in 2026 are fitted with specialized electromagnetic braking assist systems that use eddy currents to slow the vehicle without relying entirely on mechanical friction. Imagine if the car is jumping through the open doors of a moving boxcar. This is the ultimate hole-in-one stunt. The window of opportunity is incredibly narrow. At 60 miles per hour, a 10-foot wide door remains in a fixed position for only 0.11 seconds. The potential outcomes of a pillar strike, where the car hits the edge of the door frame, are almost always fatal for the vehicle. The A pillars and B pillars of the car are reinforced with 4130 chromoly steel, but no amount of reinforcement can survive the sheer force of a 100-ton train car. Data from safety tests suggest that a pillar strike at these speeds generates a force exceeding 50 gs, which is enough to liquefy the internal components of an engine and surpass the survival limits of even the most advanced safety harnesses. To mitigate this, the 2026 Chicago shoot utilized a launch system called a nitrogen-assisted catapult. Instead of relying on the car's own tires to get traction on the city streets, which can be unpredictable due to oil, trash, or uneven manhole covers, the car is attached to a high-tension cable. This cable is pulled by a nitrogen-powered winch that can propel the car from 0 to 80 miles per hour in less than 2 seconds. This ensures that the velocity v in our range equation is a constant, removing the variable of wheel spin. When you see the car soar over the Chicago L tracks, you are seeing the result of a system that has more in common with a carrier deck launch than a Sunday drive. We also have to consider the environmental interaction of the city itself. In downtown Chicago, the surrounding skyscrapers create a canyon effect with unpredictable wind gusts. Furthermore, the high-voltage lines of the electric train system can create electromagnetic interference with the car's GPS and telemetry systems. To solve this, Tyler's team used a redundant inertial navigation system, or INS. This uses gyroscopes and accelerometers to track the car's position relative to its starting point, without needing a satellite signal. If the GPS drops out for a half-second due to the overhead tracks, the INS keeps the phase-lock loop engaged, ensuring the car doesn't miss its mark. Case studies and historical trends show that the public's appetite for these stunts has moved toward long, uninterrupted takes. This means the jump cannot be a standalone shot. It must be part of a continuous sequence where the camera follows the car from the street, through the air, and onto the landing zone. This requires the follow car, the vehicle carrying the camera, to also perform a synchronized maneuver. In the Neon Drift Masterclass, the follow car was a high-speed electric buggy equipped with a carbon fiber crane arm. This car had to drive parallel to the train, maintaining the exact same phase lock as the stunt car. This is a dance of three massive objects: the train, the jumping car, and the camera car, all moving at highway speeds in a confined urban space. But even with all this 2026 technology, there is one factor that remains the most dangerous: the human element. While the computers handle the phase lock, a human driver is still behind the wheel of the stunt car to handle the save if something goes wrong. If the landing is slightly off axis, the driver must use opposite lock steering and precise throttle blips to keep the car from spinning. This requires a level of muscle memory that no computer can currently replicate. As we conclude this deep dive into the technology of synchronized leaps, we have covered everything from the lead ballasts of the 70s to the nitrogen cannons of the 2000s and the GPS phase locking of today. But we have saved the most controversial and jaw-dropping moment for last. There is one jump in American history that stands alone, not because it was perfectly planned, but because it went horribly, spectacularly wrong and the cameras kept rolling. What happens when the math fails, the safety systems break, and a car flies 50 feet further than it was ever supposed to? We are heading into the finale, where we break down the unscripted legend. This is the jump that nearly ended a franchise and created the most iconic piece of footage in the history of the United States film industry. You have seen the engineering. Now you are going to see what happens when physics takes over and humans lose control. The final part of the masterclass is the one they tried to ban, and it is coming up right now. When physics takes over and humans lose control, we enter the territory of the unscripted legend. This is the moment where the calculation on the chalkboard fails to account for the raw, unpredictable nature of the American road. To understand this final chapter of our masterclass, we must look at a date that is etched into the history of stunt coordination. October 11, 1978. In Covington, Georgia, a stunt driver named Craig Baxley climbed into the seat of a 1969 Dodge Charger. The script for the pilot episode of The Dukes of Hazzard called for a standard jump over a police cruiser. The math suggested a launch speed of roughly 65 miles per hour to clear the obstacle and land safely at the 80-foot mark. But historical trends in early practical stunts often suffered from a lack of digital telemetry. Baxley, feeling the adrenaline and the roar of the 440 Magnum engine, hit the ramp at nearly 82 miles per hour. Imagine if you are Casey, a 2026 digital forensic analyst specializing in automotive ballistics. You would use high-speed motion tracking to see that a 17-mile-per-hour discrepancy isn't just a minor error. It is a mathematical catastrophe. Because the range of a projectile is proportional to the square of its initial velocity, r is proportional to v. 2. That extra speed sent the Charger into a trajectory that was never intended. The car didn't just clear the police cruiser. It cleared the entire street, soaring 16 feet into the air and traveling a staggering 132 feet. The potential outcomes of this overshoot were nearly fatal. As the car reached the peak of its arc, it lost its horizontal stability. The lead ballast, which we discussed in previous parts of this masterclass, was calculated for an 80-foot flight. At 132 feet, the air resistance began to act on the underbody for a longer duration, causing the car to tilt further forward than expected. When the General Lee finally made contact with the Earth, the impact was so violent that the front suspension didn't just compress. It disintegrated. The torsion bars snapped, the K-member, the structural heart of the front end, was driven into the asphalt, and the driver experienced a vertical deceleration that exceeded 15 gs. This is where we must discuss the medical data of a failed landing. In 2026, we understand the concept of the secondary collision. While the car hits the ground, the driver's internal organs continue to move at the pre-impact velocity until they strike the chest wall or the skeletal structure. Baxley survived, but the car was a total loss. Yet, because the shot was so majestic, so terrifyingly high, the producers kept it in the opening credits of the show for years. It became the gold standard for the American car jump, despite being a technical failure. Moving into a different case study of unscripted chaos, we look at the 1980 film The Blues Brothers. Director John Landis and stunt coordinator Gary McClarty oversaw a jump involving a 1974 Dodge Monaco, the Bluesmobile, jumping over the open 95th Street Bridge in Chicago. This jump remains a masterclass in the limits of heavy vehicle structural integrity. The Monaco weighed over 4,000 pounds. Unlike the sleek Mustangs or Chargers, the Monaco was a massive C-body Mopar with a long rear overhang. The technical issue here was the kickback. As the heavy rear end of the Monaco left the bridge, the suspension rebounded with such force that it kicked the tail of the car upward. This initiated a nosedive that the driver had to counteract with immediate throttle input to keep the rear wheels spinning, utilizing the gyroscopic effect of the drivetrain to pull the nose back up. However, the landing was on a flat, unforgiving concrete surface. Step by step, if you watch the footage in slow motion, you can see the exact millisecond the frame fails. The rear axle housing was ripped from the leaf springs upon impact. This is a prime example of the historical trend, where the sheer mass of American iron works against the survival of the vehicle. In 2026, we analyze these moments using AI-driven simulation software like vSim 2026. If we were to resimulate the Blues Brothers bridge jump today, the software would show that the structural fatigue on the C-pillar reached a breaking point within 0.04 seconds of impact. The only reason the car didn't snap in half was the addition of a hidden internal steel spine, welded from the front subframe to the rear trunk pan. This hidden engineering is the silent hero of the unscripted legend. We also have to address the modern era of unscripted risk, specifically the case study of the 2023 film John Wick, Chapter 4. During the sequence at the Arc de Triomphe, several jumps and collisions were performed in high-density traffic. Stunt coordinator Stephen Dunleavy had to manage the potential outcomes of a multi-car chain reaction. In one specific take, a stunt car hit a curb at a slightly higher angle than planned, launching it into a side tilt. The driver had to make a split-second decision: stay on the brakes and risk a rollover, or accelerate into the tilt to use the car's own torque to right itself. The driver chose to accelerate, a maneuver known in the industry as the power over, which saved the shot and the vehicle. The data from these modern high-speed maneuvers shows that we have moved from a build it stronger philosophy to a calculate it better philosophy. In 1978, they just added more steel. In 2026, we use active suspension systems that can change their damping rates in the middle of a jump. Imagine a car that can sense it is in free fall and automatically adjust the shocks to their stiffest setting for the landing, while simultaneously retarding the engine timing to prevent a fire upon impact. Throughout this 10-part masterclass, we have traveled from the hills of San Francisco in 1968 to the skyscraper canyons of 2026. We have looked at the ballast of the General Lee, the computer-modeled spiral of James Bond, the nitrogen cannons of Christopher Nolan, and the aerial drops of the Fast franchise. The common thread in every single one of these insane moments is the relentless pursuit of the impossible. American movie history is defined by the moment when a machine designed for the commute is forced to become a bird. As we conclude this deep dive, remember that every frame of film you see is the result of thousands of hours of engineering, testing, and risk management. The car jump is more than just a spectacle. It is a technical discipline that balances the beauty of a parabolic arc against the violent reality of kinetic energy. Whether it is a calculated success or an unscripted legend, the car jump remains the ultimate expression of the American action spirit. You now have the technical foundation to look at any car chase with the eyes of a stunt coordinator. You understand the math, the mechanics, and the history. But there is one final frontier we haven't touched: the world of the hyperjump, where electric motors and instant torque are changing the physics of the launch once again. In our next series, we will look at how the shift from internal combustion to electric powertrains is allowing cars to hit ramps with 0 to 60 times under 2 seconds, and what that means for the future of the stunt driver. The era of the silent leap is just beginning, and the physics are about to get even more insane.